Alright, welcome to the first lesson in physics where we start talking about units. So units are fairly important in science. There are two main systems for units that are used in the world. The one is probably one that we're more familiar with here in the United States, the English or imperial system of units, pounds, feet, inches, and miles. The other one, if you're from other areas of the world, is actually probably more familiar to you. That's the SI or the metric system. And those are meters, kilograms, kilograms, liters, those types of units. SI and metric units are generally the units that we use in science, and there are some very important reasons for that. Here, the picture on the right, we actually have the kilogram. This cylinder weighs or is the defined unit of exactly 1 kilogram. So there happens to be only 7 base units in the SI system, and those 7 units I have shown here: mass, length, time, temperature, amount of substance, electrical current, and luminous intensity. So the ones that we'll use most frequently here, at least in the first semester, are mass, length, and time. Mass, the kilogram, length, the meter, time, the second. The other ones that are base units: temperature, the unit of Kelvin is, amount of substance, the mole from chemistry is your amount of substance, electrical current, the ampere, and luminous intensity, the candela. Now the reason to use units is really quite simple. And the reason to develop a unit system is really quite simple. We want to make sure we're communicating numerical information in the same way a reader is reading that information. If I say something weighs or has a mass of 1 kilogram, that conveys a certain piece of information to the reader. Where the metric system really comes out of, and where this kilogram, this cylinder over here really comes out of, is from France right after the French Revolution. What was happening during the French Revolution is that there was a famine, and bakers and other people who produced food products were slowly making the amount of food products smaller and smaller, but still charging the same price. There was no standard unit system. It was really hard to prove that that's what was going on. So the SI system is one of those systems, or the metric system, was one system of units developed to kind of set a standard for what the units are. The nice thing about the metric system is that there are physical standards by which each of these units is defined. In any one of these 7 base units, there is a physical standard by which this base unit is defined. There's only 7 base units in SI units, but there are more than 7 physical quantities that we can conceivably measure. And if we do mathematical operations involving base units, we end up getting what's called a derived unit. One example of a derived unit is the unit for volume, the liter, which is really based on the base unit length cubed. A liter is actually, I think it's not quite a cubic meter. It's like 1,000th of a cubic meter or something like that. Another good example is something like the unit for speed, meters per second, a length divided by a time. Now, the other nice thing about the metric system is we can change how big one of those base units are by using what are called prefixes. So I'm not just stuck with measuring things in meters. If something is really small, I could maybe measure it in millimeters, or micrometers, or nanometers, depending upon how really small it is. If something is really big, you can measure it in megameters, or gigameters, or kilometers, depending upon how really big it is. And so we use a prefix in the metric system to really signify what power of 10 am I dealing with. Some of the common prefixes are these ones in here: kilo, deci, centi, milli. Some that we come across in physics, things like nano is a pretty common one. A nanometer happens to be pretty close to the wavelength of light. A picometer, you're talking about like the size of an atom. A femtometer, you're like talking about like the size of individual neutrons and protons in the atom. When you get on the other end of the spectrum in physics, things like megameters and gigameters, you're talking about like the sizes of our solar system type units. So a megameter, mm, is really equal to 1,000,000 meters, or 10 to the 6th meters. You can use these prefixes as a way of doing unit conversions. Now, why use the SI system? I'm from the United States. I've grown up using inches and miles and pounds my entire life. Why switch? And I think of there being 4 big advantages to switching. The first of those is that it's based on powers of 10, which makes conversions between one type of length unit to another type of length unit easier. To convert centimeters to meters is pretty easy. You divide the number of centimeters by 100 and you get the number of meters. Convert the number of inches into the number of yards. Well, there are 36 inches in a yard. That becomes a lot harder to do that mathematically. You could even look at number of meters in a kilometer. Well, there's 1,000 meters in a kilometer. That's pretty easy to do mathematically. Number of yards in a mile, well, there's like 1,760 yards in a mile. That's a lot harder to do mathematically. So one of those advantages is it makes power of 10 easier. Second advantage is they're based on a set of commonly accepted base units. There are 7 units that basically set up the entire system of units that we have. Everything can be brought back to one of those 7 base units. Third advantage, it's used by the majority of the world. It becomes easier to communicate information. For doing science, one of the main reasons for doing science is to communicate our results to other people in the world and hopefully come up with stuff that is beneficial to the world. If I can't communicate my results in a way that readers can read them and interpret them, it becomes very difficult for me to continue my work. And the fourth advantage is I can create bigger or smaller units as needed by adding new prefixes or creating a new prefix. This has happened during the course of time with our unit system. Something like the nanometer or the picometer or the femtometer. When the metric system was first developed, the femtometer was, well, completely useless. Something times 10 to the negative 15th meters, that doesn't make any sense. Now we can actually use that as a unit to measure things like how big is the proton in this atom or something crazy like that. Now, the one thing that I want to point out to you guys as we're kind of working through this is that units are quite important. And the one thing I'll say as we're working through things is to always check your units. And here's a real-world example of always checking your units. And that real-world example is the Mars Climate Orbiter. What happened with the Mars Climate Orbiter is this is an object that was designed by several scientists at NASA's Jet Propulsion Laboratory, JPL. It was worked on by a group of engineers at Lockheed Martin. Lockheed Martin is a pretty well-known, famous aerospace engineering firm. If you've ever seen the stealth bomber, that was made by Lockheed Martin. So they designed this thing, and basically what it's going to do is it's going to orbit Mars, and the main reason to have this thing orbit Mars is to start to collect data on the climate of Mars, really to see how does the climate of Mars compare to the climate of Earth. This is a $328 million project. You have like about a $100 million satellite here, but you have the rocket to get it into orbit, you have the people's time to build it, you have the time to design and test it. So this is like a large sum of money here. It actually took 6 years to design and build this thing. It was launched in 1998 and crashed into Mars in the middle of 1999. This was probably one of the biggest failures that, well, NASA has had, at least in recent memory. The one thing to point out about sending things to Mars is, while that may seem like a relatively easy thing to do and something we do all the time, it actually happens to be a relatively difficult thing to do. I actually looked up some data, and of the 50 some odd things that we as a race have tried to send to Mars, almost half of them have failed in some way, shape, or form. This one failed by smashing into the planet, which is a pretty epic failure. So what the heck happened, and how does this relate to units? Well, here's what happened. Lockheed Martin engineers, the people that built it, used English and Imperial units to both design the spacecraft, also to develop the computer program which is going to control several maneuvers in the spacecraft. One thing to point out about sending something to Mars is you can't control it here on Earth. The reason why you can't control it physically here on Earth is that it takes 15 minutes for you to send a signal from Earth to something in orbit around Mars. Well, if you're trying to control this thing by a joystick, whatever move you make is going to happen 15 minutes later on Mars. And any data you're seeing on your computer screen is already 15 minutes old, because it takes 15 minutes for that signal to get back to Mars to here. So that means if you see something and you say, move the orbiter out of the way, it'll take 30 minutes for you to see it and for you to get the command back to the orbiter and move it out of the way. For something that's moving at hundreds to thousands of miles a second, well, that doesn't work very well. So the thing has a computer on it which will do all the maneuvers that it needs to do. One of the maneuvers is what's called an insertion maneuver. It's basically the maneuver which slows the spacecraft down and gets it into orbit. Well, Lockheed Martin used imperial units or English units as the commands to this maneuver, but never included what those units were in their computer program. NASA, and this is specifically the Jet Propulsion Laboratory, uses SI units in all of their space programs. The reason why NASA uses SI units is that they communicate with other nations who use SI units for things like the International Space Station. Even in 1999, they were communicating with other nations and were required to use SI units as a part of that communication. Now, one thing to point out is that nobody at the Jet Propulsion Laboratory, first of all, looked at this program and said, geez, these commands don't make any sense. And nobody at Lockheed Martin said, hey, we're doing this in English units and not metric system. Basically, no one on either side bothered to check the unit. The joke that I have here is that Lockheed Martin engineers learned to check their units on this day in 1999 when their Mars orbiter smashed into the planet because they put the wrong units in the computer program. So the lesson for you is always check your unit. While many of you, at least in this class, are not going to be dealing with $300 million Mars orbiters, you might be in a situation in the future where you are dealing with something like this, and knowing what units you're working with is very important. And for the sake of our class, using units can be very helpful in determining, is this a reasonable answer, is it something I should get, or am I completely off? That's a quick overview of units and how they work and why we use them, and this will conclude the first lesson.